I'm also going to record it so that I don't have to do it. So we're starting on, what page is that is? So page 10 of your booklet on 2.1, I believe, or it just says chemistry chapter 2, I believe, altogether. So we're going to try and finish this chapter this week. It shouldn't take us too long. There's 3 sections, but I'll try and go through as much of 2.1 today as possible. The review video is on the Google Classroom, so look at that to review what we've done in the past. And if you haven't taken Science 20, then you've never done it, so really watch that. Because there is some bio 20 people who are in Science 30. So this is a review, and something to really always be looking back on, and I should open it up, is your data booklet. So if you go to your Science 30 data booklet, that is something that you should have on hand, and I think you need to be on page 9 of it. I'm just going to search for it here so that I can open it up. So this data booklet, page 9, I'm already on it because I was doing organic the last time I opened it. So that's where you're going to use all this information to be able to name this stuff. So let's try this first example. So it says, write the systemic names for the following hydrocarbon compounds. I just want to zoom that in. Perfect. So the very first one there, it is, it's got 2 C's and a bunch of H's. So if you remember how we would name these, we have a bunch of different ways, and I'm going to show you how you can find them on your formula sheet. But if you go on to your formula sheet, there's the first 3 are the ones that we've reviewed, and those are the ones we did last year. If you go over to examples of them, the big difference between them is the first one has single bonds, the second one has double bonds, and the third one has a triple bond. Okay, so that's the difference between those 3. So if we look at the first one that's a single bond, they're called alkanes. Okay? And what that means is that the ending of it is ANE. So if you look at this on your data booklet, you can see, oh, an example, single bonds. Okay, that's an alkane. Alkanes, we just use that ending of ANE. Okay? So, go back over here. The first one is a 2-carbon chain, right? It's got 2 carbons, and there's no double bonds there. So, because there's no double bonds, it would be an alkane. So I'm just going to write that on the side of here, just so you know, but that's definitely not the name of it. That's just what we're going to use, because we need this ending to name our alkane. Next, our next step is to figure out how many carbons are there. So we count out our carbons, and our chain is 2. So we go over to our table here on our data booklet, and we can look at this little table at the top. The italics indicate the numbers. So meth is a 1 carbon, F is a 2 carbon, and so on. All right. So if we look back to ours, we've got a 2 carbon, which means it's an F. So 2 carbons means that the prefix of it is F. And then because we know it's only got single bonds, that's going to be an ethane. Okay. So that's a pretty straightforward one. They become a lot more complicated than that, but that's a review for you. If you want to review more, you should go back to that review video that we looked at last week. Okay, let's do the second one here. So right away I can see on the second one that there's a double bond. So right here, double bond. That double bond tells us that it is a ENE ending. Why? Well, this is a double bond right there. If we go back back over, that's an alkene. So we use the ending E and E. So right underneath this, I'm going to write alkene, not with the highlighter. And that ending E and E is what we're going to be adding to our molecule. So now we've got to count out the number of carbons. How many carbons we got there? 3. So if we don't know, we go back over here, back to our top of the booklet, and a 3 carbon is right here. That is prop. Okay? Not propane, because our ending is E and E. It's actually propene. Okay, so if we're using that first prop, and then we're using that ending E and E. Okay. We're not done. Something that's special about double and triple bonds is we gotta tell you where it is. So we have to tell you where that triple bond is. Double bond in this case, sorry. So how we do that is we need to count out the carbons, and I'm going to do this in red. So we can count from left to right or right to left, it doesn't matter. I'm just going to do it both ways, 1, 2, 3, or we can count this way, 1, 2, 3. So because this double bond is between these two, if we use the bottom, which is 1, 2, 3, right to, or left to right, we would say that that double bond is connected to the first carbon, number 1. If we try the other way and we count 1, 2, 3, then we're saying that it's connected at the 2, because 2 and 3, we always use the lower number. So what we're doing here is we need to find the lowest number. The lowest number is going to be 1. So I'm not going to count that way. I'm going to count left to right and go, well, the carbon double bond is between the 1 and the 2, so we just write 1. It's on the 1. So how I do that is I write it right above, right in front of propene. So I'm going to write 1 dash propene. So that 1 tells us, well, it's a double bond between the carbon 1 and the carbon 2. Does that make sense? Is it ringing a bell? Do you remember this? Okay. So that is something that you will need to get familiar with. But once you get a hold of these things, it's like, I don't know, I think it's, once you get all the rules down, then you're just like, oh yeah, I don't have to do much thinking here, I just gotta go through all these steps. They sometimes take a little while, but that's why my videos sometimes is so long of doing the review, because I'm spending so much time explaining all these. So I might have to stop halfway through this.
Is washing speed?
Yeah. Just make sure you take a whole pass. So draw the structural diagrams for each of the compounds. So we went from structures to words, now we're going from words to structures. Okay? And this is reviewing some things that were in the review that you haven't seen yet on this. So they want us to draw 2,2-dimethylpropane. How the heck are we going to do that? Well, our first step is to figure out what propane is. So I sort of work my way backwards. I start at propane, then I look at methyl, then I look at di, then I look at the 2s. Okay, so propane. What is propane? Three. It's at 3 carbons. So this propane, that's what we're looking at right now. We are going to draw 3 carbons. So I'm going to draw them like this. Do we need any double or triple bonds? The answer is no, because that is an anion, propane, that is an alkane, so it doesn't require any double or triple bonds. Okay, so that's good. We're done with propane. That's all we need to do there. We need to look at what the heck does dimethyl mean. So that's something that was done in the review. Methyls, or alkyls, I'm going to show you right here. They're called alkyls. Those are branches. So branches off of this called alkyls, so they use that YL ending. And then they use the same prefixes we've been using. So if it's a methyl, meth means one. Okay? Carbon. So we have a methyl, but this is a more difficult one because we've got that di in the front. Do you remember what di means? What number that means? Back to your other chemistry knowledge. Mono, di, tri, tetra. Yeah. So if you forget that, it's also in your data booklet. Like, you have so much time on your exam, you can take 6 hours to write it. There's so much information in this data booklet to help you out. Right here, prefixes, di. You see that there? Number 2, right there. Top. Okay, so that tells us there. So what this is telling us is there's 2 methyls. Methyl is a 1 carbon branch. So there's 2 of them. And where are they? It tells us right there. Sorry, and my throat is really dry. I don't know COVID. Try some Sunday. Okay. 2,2 dimethyl. So what that's all saying is we have 2 methyls. They're at the number 2. So we've got to count 1, 2, 3. Should be using that terrible marker, but the number 2 is going to be in the middle regardless of which way we go, right? So what that's telling us is that we need to draw our dimethyls on the middle one. So we're going to go like this, and we're going to go like this. And that is it. I do not need you to draw the H's, but know that wherever it's connected to, if it doesn't have anything connected, technically there's an H here, an H here, an H here. So every sign that doesn't have anything on it is an H. We just don't draw them because who wants to draw that? That takes too long. So just remember that that's what it is. These are called hydrocarbons. Jeez, I need water. So hydrocarbon is hydrogen and carbons. So every time we have a carbon, they are connected to either a carbon or a hydrogen. Okay? Is that okay, Nevis? So then, is there one more in here? Doesn't give us a lot of room. I'm just going to erase this temporarily. I mean, hopefully you got it in the video if not. Go back. Okay, so we're going to do the last one here, which is 2-methyl-prop-1-ene. Something I've got to note to you is that this would actually be, this is an old way of numbering, and I really got to update this. This would actually be 2-methyl-1-propene. So let's name that instead. Because back in the old days, back when I was in high school, they used to put the 1 in between the prop and the ene. Now we just put it in the front. That 1 is telling us how many, or where the double bond is. Okay, anyway. So our first step is to draw propene. Prop is how many? 3 carbons again. The ene on the ending, ene, is telling us, if we go back to here, an alkene has a double bond. So what we've got to do is we've got to put a double bond. Where do we put it? Well, this number is telling us. Right? That number ahead is telling us that we're putting it on the 1. So we're going to put a line there. Now it's a double bond. This seems like how that looks. Okay, so that's done. We've done up to, we're done with that part. We've drawn it. We just need to deal with the 2 methyls. Or no, the methyl that is on number 2. So that 2-methyl is not saying there's 2 of methyls, like I said. It's saying that there's 1 methyl at 2. If there was 2 methyls, then it would say dimethyl at 2. they would actually say dimethyl and then say 2, comma 2, like it did in the first question. But we only know one methyl. So what's a methyl? One carbon chain branch. So, and it's at number 2, so we would put it there. It doesn't matter if you put it up or down. You could put it there and not there. I don't care. It doesn't matter. In life, like these things could move around, and that doesn't really matter where they are. Okay? So that's what that is, a 2-methyl-1-propene. Sounds very confusing, but when you draw it out, it's not that bad. It doesn't look too confusing once you actually draw it. It's just a lot of words. So break it down into its sections. That's why I like to, I do one part and the other, and that seems to help. It helps me at least. I don't know what helps you, but okay. So that's reviewing what we went over in that first section. So in that review video, that stuff we should have done last year. If we didn't, then my bad, but continue. We need to continue off that information. In the review video, I also showed you how to do a benzene, but this is explaining it. I don't think we did that last year. It was just randomly in there. Anyway, a benzene ring, what that is, it says it's a hexagonal arrangement of 6 carbon molecules, and the ring is arranged like this. So if you ever see a word benzene, you have to always draw that. Okay? That seems very complicated, but if you see it sometimes written somewhere else, they don't write the H's, and they just write C double C single C double C single. That's not enough carbons. C double C single. That's a really bad. But you get it, so they don't draw any of the H's, they just draw that inside. I can't, that's a terrible drawing, and I don't want you to look at my terrible drawing. Also, sometimes you will see it where they draw it like without any C's. And you probably will see these online if you ever look it up. They'll just draw it like 1, 2, 3, 4, 5, 6. And then what they'll do is like a double bond, single bond, double bond, double bond. And they'll just draw it like that, not squiggly like mine. Those are supposed to be straight lines. But they won't even draw the carbons. They'll just say there's a double bond, then a single, double bond, single, double bond, single. Okay? That's a benzene. Does it say it on your sheet? I'm not sure. It does not. So that is something you just have to remember, unfortunately. The sheet gives you so much, but not that. So you need to remember a benzene ring, or a benzene is a ring, and it looks like this. So an example of a benzene, it says benzenes may have alkyls or other functional groups as branches. So if you look at this one, here's an example where it's a benzene and then it has another branch off of it. So this is another carbon with then 3 H's. Okay, so if you see it written like CH3, what that really means is it's like that C, that, and then it's got C and then 3 H's off of it. Okay, does that make sense? So they're just writing it in a different way. More just to save space. Like, I even don't have enough space to draw this, but that C, this C has this C and then the 3 H's that come off it. Okay, so it's just a different way. They call that the structural formula, and you don't have to necessarily know the difference. You just need to be able to understand that means what that means. On an exam that they had in the past, when I taught this class, okay, it brings us to here, because this was a question on an exam about aromatic rings. So benzene rings may also be called aromatic rings or phenyl rings. There was a question on an exam. What aromatic ring means is that it's really smelly. It has a smell. It doesn't necessarily be a good or bad smell, but it has a good smell to it. And we actually had something in there that was a benzene. I don't know if you remember coming to this class before and smelling like almost like mothball smell. If you ever was in that room when we had it, it's last year, it smelled like mothballs. It was even in a container, inside a bag, inside a cabinet, and then inside that door, and you could still be walking out here and you could smell it. So that's an aromatic ring, it's a benzene ring. It's what they use in most of your stuff that you buy, like shampoo or body sprays, all that stuff. So that's what they use to make benzene rings have, they're smelly. I'm going to write smelly. That's all in your own interpretation on whether it smells good or bad. Okay? And so benzenes demonstrate resonance. The extra electrons are shared by all of the carbons. In other words, the true structure cannot be accurately represented by any one structure. So what that means is, basically, we could just spin it around. Resonance means that the molecule has a bunch of orientations. And if you don't understand what that means, so if we have the double bond here and the single bond here, like my terrible drawing is 1, 2, 3, 4, 5, 6. Bad drawing. The point is that this drawing, what I'm saying is this C at the top has a double bond to the left and a single bond to the right. Well, it's the same thing if I wrote it like this. You know what I mean? Like, so it doesn't, what it's saying is it can spin in any direction. If that makes sense? Like the way you're looking at it, it could be, as long as it has 3 double bonds and 3 single bonds, then it could be in any orientation. That's just like when I showed you back on this last slide. No. Last slide. When I showed you this here, remember how I said that you could draw the C on the top or the bottom? Doesn't matter. That's exactly what I mean by the benzene rings. It doesn't matter the orientation, where we draw the C's and the double bonds and stuff like that. It could be in many different ways, and the word for that in chemistry is resonance. So if something can be drawn in different ways, but it's still the same thing, that's called resonance. Have you ever heard someone say that, like, cheese whiz is like 1 molecule away from being toxic? Okay, well, that's what they have heard. And cheese whiz is actually 1 molecule away from plastic. I think margarine is too. And the reason the 1 molecule is like a resonant structure. So if we have it one way, it's cheese whiz. If we change it, then it's plastic. You know what I mean? So just the orientation of that structure can make it different things. And maybe that makes it more complicated. Anyway, these things are not good for you. But the general thing is benzenes are not good for you. So when we have smelly things like our shampoo, I'm just holding it right here, but I can smell my shampoo. It probably has benzene rings in it. Not good. You want to try and find things that are naturally sourced, hopefully. So using like natural shampoos, things that have like essential oils that make the smell as opposed to chemicals. Because we don't want to just put chemicals on our body all the time. We do that every day. We put creams on our body that might have chemicals in them. We wash our face with chemicals. We're putting so much chemicals, and these benzenes are pretty bad, or they're bad for us. They can lead to respiratory problems. They can lead to nervous system problems, stuff like that. So benzene rings is not good. I hope that doesn't make you scared. Yeah, this is what they might look like. See, this picture is much better than me. My picture of showing how it didn't have C's and had squiggly lines, that's what I was trying to show. So you might see it drawn like this or this. That's a benzene ring still. So any sort of hexagon, okay, is a benzene ring. Problems with benzenes. Well, they naturally occur in petroleum and coal. So these are in gas and diesel, and it's a mixture of hydrocarbons, including aromatics. Have you ever smelled gas? got a strong scent, right? You can't get gas off of you. That's because it has benzenes in it. There's evidence, I guess I already went into this, but there's evidence that benzenes are a carcinogen. So that means that it can cause cancer. So there's lots of evidence that shows that benzenes are a cause of that. So this has led to the decrease in the amount of aromatics now present in gasoline. So they try to take some of those benzenes out. This is just talking about gas, but what I was talking about in your cosmetics and stuff, try and go for things that are less scented. You know how some people get like rashes from using certain laundry detergent? They need to use like the unscented stuff. And that's because people are allergic to these benzenes. And it's your body telling you like, no, don't put this on me. It's a chemical, it's bad. Like it's better to have things that are like unscented and naturally scented, like I say essential oils. Like I use natural deodorant. I started doing that like a couple years ago because I realized that there's so many bad chemicals in deodorants that are bad for your body. They have aluminum, like metal, and it blocks your pores and your armpits. So yeah, that's one thing I've changed in my body, but and I always try and find things that are more natural. Like even, where's my keys? My favorite store, I'm not trying to be like a commercial for the store, but it's natural. Rocky Mountain. Have you ever heard that store? Rocky Mountain? Try some of that, see if it's nice. So it uses all natural things and organic as well, some like chemical free. But I don't know if you like lavender. It smells good. As opposed to smelling like alcohol, right? And it sort of moisturizes your hands too. Yeah. So these sort of things, they're there's lots of companies out there that are trying to make things that don't have benzenes because we know the benzenes are bad. That's why like sniffing gas is bad, right? Because that's not good for your body. As far as gasoline and oil spills, it says some aromatics are soluble in water, and this leads to the concerns about these compounds leaching into the water systems when there's a petroleum spill. When there's a spill on the ground, it must be cleaned up through the process of remediation. So this is a breakdown of hydrocarbons. What that all means is, I don't know if you've ever tried to mix oil with water. It doesn't work. And I think I did that with the science buddies in the other cohort, but one day. We just tried to mix oil with water, didn't work because there are different types of molecules, polar versus non-polar. But we don't need to know that. All we need to know is that in order to clean up an oil spill, we're going to have to try and break down those hydrocarbons so that they can be soluble in the water. So we put oil on the top of the water in its own state, not going to work. To get rid of it, we're going to have to break down those molecules. Just like in combustion reactions. I think that's what you asked me this morning. Is that a question? You asked like combustion. Combustion reactions. So that's a good way of getting, maybe it's not a good way because they would leave carbon dioxide, but if you had oil on top of water, you could burn it off. That is a way. So if we had a big oil spill and you could see oil on the top, we could light it on fire and it would burn, break apart those molecules. Not normally how they do it, but oh wait, you could. So we need to break that stuff down. So linear compounds can be broken down quickly by certain soil bacteria, and cyclical compounds like benzenes, because they're hydrocarbon rings, those take a lot longer to break down. So those are things like persistent organic compounds or POCs, things that are in lots of chemicals, paints, all that stuff, these chemicals that are harder to break down. So all this is saying here is that things that are in a straight line, like, I don't know, I'm just going to pretend this is in a straight line. So something like this, like propane, straight line, easier to break down. Something like benzenes, you can draw as you go. That's not a benzene, that's fine. Regardless, anything that's in that circle, hard to break down. So hard to break, the first one, not so easier, and there's different bacteria in the soil that'll actually naturally break it down. I think we did questions about that in Science 10, about soil remediation, but I don't know, maybe bio. Anyway. Benzenes in food. So incomplete combustion of oils in food can produce polycyclic aromatic hydrocarbons. Think charred steak. So if you like things burnt, that's actually bad for you. Because that's leaving that incomplete combustion. You're like burning your food and it's actually not good because you're getting those benzenes into your body. So people, do you know people that like burnt stuff? Do you like burnt stuff? My dad likes to eat, I don't think he likes it, but he will eat burnt toast. Like when I was a kid, if I got when I was toasted too long, he'd be like, oh, I'll take it, and he just eats black toast. So that's not good for him. That's an aromatic, it's creating benzenes in your food, so don't burn your stuff. That's what I'm saying. Okay? But then cook it long enough so there's no bacteria in your steak. PAHs, that polycyclic or aromatic hydrocarbons, are also found in particular emissions from combustion of hydrocarbons. There's evidence that PAHs may interact with your DNA and cause mutations. So there's some evidence that shows that by having these around, they can cause mutations, and mutations normally lead to cancer. So these are things, chemicals in our surroundings that's not good. So don't burn your food if you don't want to mutate yourself. There's two questions that have to do with this section, so not too bad. Or that part of 2.1. So I'll stop there right now. You guys can work on those two questions, and then I will come back to this section. Is that okay? Is everything okay so far? I'm sorry. I feel like you look tired. Am I making your brain hurt?